Hi guys, what I want to do in this lecture is just go through the 2.2 in case you're watching virtually, or to go back and review. So in this lecture we're going to talk about the strength of ionic bonds, and usually how we apply that is who has a higher boiling point or melting point or something like that. We'll look at the potential energy in bonds as well as bond energy and bond length. So the strength of ionic bonds are super strong, so it's going to require a lot of energy. And when we put energy in, it is endothermic. Part of the reason why the melting points are so high is that ionic compounds exist in crystal lattices. Like if you have salt, salt does not exist as single NaCl units. The sodium ion is surrounded by 6 chloride ions, and every chloride is surrounded by 6 sodium ions. And so you're going to have to inject a lot of energy, 788 kilojoules to be exact, to break a lattice like that. And part of the reason why is because each ion has 6, it's attracted to 6 things of opposite charge. So it's going to require a lot of energy to melt or vaporize ionic compounds. So factors affecting the melting points, here's our old friend Coulomb's law again. And so from this equation, you should be able to see that the melting point, if we compare ionic compounds to each other, the melting point is going to increase as the charge of the ions increases. That's this part right here. And as the distance between the ions decreases. And so using Coulomb's law, you can predict comparisons of melting points of different ionic compounds. The stronger the force of attraction between the ions, the higher the melting point. And so this says which compound from each set has the greatest melting point and why. Okay. I do have it. Okay. So which compound from each set has the greatest melting point and why? And so we have lithium fluoride and lithium iodide. If you take a quick look at the periodic table, iodine is a bigger ion, and fluorine is a smaller ion. So given that, what would you say? So our distance, think about the distance has increased, so our numerator has gotten bigger, so that force is less. So I hope you would have said that LiF would have the greatest melting point. And so the reason why LiF, the fluoride ion, is much smaller than the iodine ion. If you look at magnesium chloride and magnesium oxide, if you made a prediction, think about charge in this case, all right? Here we have magnesium is a +2, and then our chloride ions are charged -1. Magnesium here is a +2. Oxygen is a -2. Based on that, hopefully you would predict that MgO would have the greatest melting point. And then we have sodium fluoride and magnesium iodide. Okay, so we have sodium is a +1, fluorine is a -1, magnesium is a +2, iodide ions are a -1. And so again, for the charge reason, I would predict that MgI2 would have the higher melting point. So greater charges are always more significant than smaller distance. The AP exam and your unit exams are going to have questions like this. And then remember, you're going to have to explain why, as you did on the last test, one ion is smaller than another. And so the fluoride ion is smaller than the iodide ion because the iodide ion has more protons, it has more electrons. Those electrons are further from the nucleus. And so the force with which those electrons are attracted to the nucleus is less in the iodide than in the fluorine. So looking at a diagram like this, it says which of the following metal fluorides would have the highest melting point and why? So we have this guy's bigger, okay? So some things that I notice is that these are bigger. The red ones seem to be the same. And so I would predict that the smaller one would have, because it looks like there's a 1-to-1 ratio. So it looks like ions both have a -1 charge and a +1 charge. And so the cation, the compound that contains the cation with the smallest radius, is going to have the highest melting point. So B would have the higher melting point. The ionic charges are +1 and -1 for both compounds. But the metal cation, B, is going to have the smaller radius. So looking at bond energy, this can be actually thought of in terms of gravitational potential energy. So if you have a rock on top of a cliff, it's going to have a lot of potential energy. Its potential energy is going to decrease as it falls. And then the rock's potential energy is at a minimum when it reaches the bottom of the cliff. So an application of that then for our atoms are that the potential energy of valence electrons decreases as they approach the nucleus of another atom. Bond energy, when energy is released, energy is going to be released during the formation of a bond. And so when the bond is formed, the potential energy is going to decrease as the atoms move closer together. The same amount of energy must be added in order to break that specific bond. And so then potential energy increases as the atoms move away from each other. So the amount of energy required to break the bond between two specific atoms is going to be equal to the amount of energy that is released when a bond forms between the same two atoms. Remember, when we yep, okay, never mind. Kill that thought. Okay, so it requires 432 kilojoules per mole of energy to break the bonds between chlorine and hydrogen, and 432 kilojoules per mole of energy is released. This is our law of conservation of energy. This diagram is a favorite of College Board. So basically this graph is going to show the formation of a covalent bond between two individual hydrogen atoms. And a bond will only form if the energy of the aggregate, or the two together, is lower than the combined energies of the two separate atoms. So the energy term is a combination of the kinetic energy of the electrons and the potential energy resulting from proton-electron attractions and electron-electron and proton repulsions. So as the atoms move closer together, notice that the energy decreases. And so the kinetic energy of valence electrons is going to decrease as attractions for the nucleus of the other atom increase and their motions become concentrated in the area between the nuclei. So our kinetic energy here, our kinetic energy is going to decrease, and our potential energy is going to decrease as attractions between the nuclei and the valence electrons pull the nuclei closer together. The energy that is lost is released as heat during the formation of the bond. And the energy that is lost during the formation of the bond is equal to the energy required to break the bond. So at 0.074 nanometers, the bond length of H2, the energy is going to be at its lowest point. So basically, this is the universe thrives on the lowest energy systems. So basically, that's how hydrogen exists. And moving further to the left, if you think of this as a spring, right? If this is average, if you moved further to the left, then that would be like compressing the spring, and so the potential energy would go up. So potential energy is going to decrease as attractions between the nuclei and the valence electrons pull the atoms together. I think I just kind of explained that to you in the last, the visual slide kind of thing. At 0.074, to go back to that previous slide, kind of showed you that, the bond length is at its lowest point, okay? And moving further left, the potential energy is going to rise. As the atomic radii of bonding atoms increase, the bond length increases. So this is a good statement. The bond length increases and the bond energy decreases. Hopefully this makes sense. Closer proximity to the shared electrons is going to allow for a stronger force of attraction between the protons and the bonding electrons. And when the force of attraction is greater, it's going to require more energy to break the bond. So shorter bonds equal greater energy required to break it. And so here, if you kind of take a look at bond energy and bond length, we have carbon, and it is being bonded to chlorine, bromine, and iodine. So our radius, our atomic radius, is getting bigger as we kind of go down this list. They are all single bonds. They are all the same type of bonds, but the Ci bond is going to be longer than the CBr bond, and the shortest bond in this group is the carbon and the chloride. And notice the bond energy, okay? We're going to have our highest energy with our shortest bond. As the atomic radii increase, bond length increases. Potential energy, so if you're asked about that, but a lot of times you're asked about bond energy. So the bond length increases as our radius gets bigger. Our potential energy increases, but our bond energy decreases. So consider these space filling models. So which model has the least amount of potential energy? So the way I always look at this, I say least potential energy. That means it has more kinetic energy or more energy, and the one that has the most energy is going to have the shorter bond. So shorter bonds have higher bond energy. Higher bond energy is lower potential energy. So between the two, who has the lowest bond energy, or I like to think in terms of, and this is the lowest bond energy. So this guy is going to have our lowest potential energy, and this will have a higher potential energy. So this will have the lowest potential energy and highest bond energy. And this will have a higher potential energy and a lower bond energy. So now I can answer the question, so which model has the least amount of potential energy? That's going to be model 1. And which one has the lowest bond energy? That's going to be model 2. Hopefully that helps you a little bit in how to think about it. Okay. And then as the number of bonds between the two atoms increases, the bond length decreases and the bond energy increases. So a single bond is our longest bond, our double bond is shorter, and our triple bond is the shortest bond. So remember, as bond energy increases, potential energy decreases. So as the electron density between the positive nuclei increases, the attractive forces between the protons and the bonding electrons are going to increase. And it's going to take more energy to break apart something with a triple bond than it is a double bond or a single bond. And so we can see here, this says the number of bonds between the two atoms increases. So if we have fluorine looks like this, oxygen looks like this, and nitrogen looks like this. So these are our shortest bonds. So highest, I like to look at it as kinetic energy, highest bond energy, even though it's not really energy of movement. So our highest will be our lowest potential energy. And so we should see the highest bond energy, and indeed we do. Bond order is the number of bonds between the two atoms. So when the bond order increases, the bond length decreases, the potential energy, we had said that. So if this is our highest bond energy, or for the purpose of my argument, highest kinetic energy, it's going to have the lowest potential energy. Hopefully that makes sense. So here's a little model here. It says, consider the ball and stick models below. The carbon-carbon bond in which molecule has the lowest potential energy, and which has the lowest bond energy. So we have a triple bond here, and we have a double bond. So our triple bond has, these are shortest, these are shorter. Shorter is higher bond energy, which would be lower potential energy. These guys are longer, less bond energy, more potential energy. So now I can look at the question. So which molecule has the lowest potential energy? That's going to be 1, okay? And which one has the lowest bond energy? That's going to be model 2. So these are space, these are ball and stick models. There we go. So a space filling model is going to show differences in the radii and relative bond length but it doesn't show like the 3D positions. The ball and stick, which is what these guys are, that's going to show the 3D position of the atoms. It's going to show single, double, and triple bonds. The thing to remember about these is these little balls are not proportional to the size of the atoms. I think a space-filling model shows you the size of the atoms in relation to each other a little bit more. Hopefully that's helpful. So add this information to your notes and then work on the problems for 2.2 are going to ask you to compare different kinds of ionic compounds in terms of which will have a greater bond energy, which will have a higher melting point and things like that. As always, if you have questions, feel free to email